Started. People can cycle in as they want. Thank you all for coming. I'm Sarah. I'm here with Suno, and I'm going to be talking a little bit about the technical evolution over time of music AI and how I use Suno as a musician to make music. So a little bit of overview for the talk. First, I want to talk a little bit about why we would ever want to use machine learning in music, like what are the use cases for musicians. I'm going to talk about the evolution of generative music over time, how we've gotten from like really simple algorithms to the deep learning methods we use today. I'll talk a bit about the current state of the art in music AI, and just going to let you all know now, I'm not going to talk about the Suno architecture. I'm going to talk about research that's been published that will give you just like a good sense of the field. And I'll share a little bit about how I use Suno as a musician. So just to introduce myself, I'm Sarah. So I am a performer. I perform electronic music with my guitar and laptop. I use a combination of tidal cycles, live coding with Gen AI and electrical guitar looping. So this is me performing in New York last year. Currently, I'm an ML engineer and artist in residence at Suno. So that means I work on our music AI models and also make music with our models. I'm a classically trained guitarist. That's what I studied in my undergrad, and have about 7 years of experience in audio ML, everything from speech enhancement for hearing aids to designing digital instruments to now mostly focusing on deep learning and Gen AI. So first let's talk about like why would we ever want to use machine learning in music? A couple of things. I think that these systems are really powerful for idea generation. So, if you have a melody in your head and you're kind of thinking for different ways to expand it, I think it can be a really good like creative partner in that way. You can explore different ways to connect phrases or continue one, or maybe you will just use it as an inspiration for a melody to turn into a full track. You can also use it to quickly realize a simple melody into different genres if you want to audition your track in different genres. It's really nice for polishing and auditioning ideas. So with Suno, if all you know how to do is hum or sing really badly or tap a beat, that's okay. You can upload that as audio input and turn it into a full track. I'm also really into the idea of AI as like a performance partner, like a model responding to what you're doing in real time to act as an improvisation partner. Instead of like improving with a person, you could play with an audio AI model. And finally, software instruments and timbre transfer. So if you've ever used a DAW, you've probably used a synthesizer or a sample-based instrument. AI can help make these easier to create and can also make like unique timbres that you can't create with any other type of instrument. So just in summary, I think really the goal is to enhance human creativity and composition. We're not trying to replace it. I think a lot of these models can generate really surprising output that can inspire you creatively. I know that's definitely the case for me. So now let's do a little step back in history through how generative music has changed over time. So the idea of like generating music with an algorithm is not new. Like even since the 1700s, people were like creating randomized melodies by like rolling dice and having that influence notes. In the 1950s, a lot of people were doing generative music with Markov chains. I'm assuming a lot of you are already familiar with what a Markov chain is, but just a quick refresher. You can think of it as a graph where each state is a note and the edges are probabilities of moving from one note to another. So in this example, you can see like, let's say we're on the note E, maybe we have a 70% chance of going to an A and a 30% chance of playing an E again. So you can actually create like a really simple generative architecture for a piece by just taking note of all the transitions in a piece and turning that into a graph. Then in the early 2000s, things started to pick up with RNNs and specifically an architecture called an LSTM. Google Magenta was doing a lot with this in like 2014, 2016 for generating symbolic music. And then, of course, everyone is familiar probably with the current state of the art, which is transformers, which came out in like the late 2010s. And also people have been using diffusion for generation as well. So we're going to cover all these things. So we'll start out with like rule-based generative music and Markov chains. So this is a quote from one of my favorite composers, Brian Eno. He had this idea that all of his ambient music is based on the idea that it's possible to think of a system or a set of rules which, once set into motion, will create music for you. So rather than composing just like a static piece, he would do a lot of composing a system that would generate a piece that was different every time you heard it. One of these pieces, Generative Music 1, this is like one of his rarest pieces. I think there were only like 1,000 copies of it. It was like a floppy disk only title that you needed a specific computer and sound card to run. And you would boot it into your computer and it would like generate music for you and it would sound different for everyone that played it. And also, early on in my career with music AI, I started using Markov chains to generate my own composition. So over here on the right, this is the score from the first generative composition I ever did back when I was an undergrad. So the idea was it was supposed to be like a real-time loop between a keyboard player and an algorithm. So like algorithmically, it was super simple. I just had someone playing piano. I was capturing all their note transitions, adding a couple embellishments, and keeping a live tracker of like the current Markov chain. And then that Markov chain would then generate new phrases and play it back for the performer. There was also a guitarist playing, and someone had control over like a couple different parameters of the algorithm. There was also like drones, and the score on the right is basically because I realized you can't just like tell a bunch of musicians like, hey, interact with this AI system and have fun. You have to give them a bit of structure. So the score on the right is just kind of mapping like the density of the piece over time, what key and notes to play, and some sections of the piece where the algorithm would solo. So I'll play like a short snippet of it. It's a little bit more on the avant-garde side. One sec, audio issues. Oh, it's coming through the Zoom device.
Oh, you can click LGTV.
Okay. Yeah. Yeah. So, is there no sound on Zoom then?
Yeah. Hmm.
Yeah, I don't know. I can try resharing the audio on Zoom maybe.
Are there any more sound demos?
Yeah, there's a lot.
Oh, hmm. I feel like maybe just prioritize people for some.
Okay. Yeah, let me check what the Okay, cool. I think we're on this right audio device. Is it possible to turn the TV volume up actually?
Yeah.
Okay, cool. Yeah, so as you can hear, like you kind of have to lean into the avant-garde and weirdness with some of these early models. But what I like about Markov chains is like their instant responsiveness, very easy to interact with. And then let's talk about how we go from like Markov chains to deep learning. So Markov chains, very little training data required. You can train it on just like a single song, but the context window is really short. You'll only get like 1 to 3 notes of context. It's super fast, but the quality of the output is pretty low and is only going to have service level patterns. So I'm going to play a piano piece that was generated with a Markov chain, and maybe some of you will actually be able to hear from it what piece it was trained on. Does anyone know, recognize? Yeah. Yeah, it's the minuet in G. Yeah. So contrast that to deep learning models, which are trained on thousands of hours of audio. Their context length can be several minutes to infinitely long, but they're super expensive. and the output quality is very high. So this is like a Suno generated piano output. Yeah, so kind of night and day difference there. And so let's talk a little bit about how we get there. So how do we train some of these models? So first of all, I just want to clarify that creative AI is a pretty hard problem. Machine learning models like this always rely on an objective function. We need some quantifiable metric of how good a result is. And for a lot of tasks, this is obvious. Like the answer is what items are in this photo or translate this sentence. Like there's a correct answer that exists. But we don't have a metric for what makes art or music good. It's subjective and people have different tastes, and it's just kind of like you know good music when you know it. So sure, we can measure similarity to the training example, but this doesn't necessarily equate to like novel, interesting, or catchy music. So let's get into the next thing on our timeline, which is RNNs. So these are trained by, you can think of music as a list of discrete events, like MIDI or notes. And here you're determining the likelihood of the next note based on previous notes. Doesn't know anything about chords or scales. It's just looking at patterns in the training data. So our RNN is fed in input of what's been generated so far, and it outputs a probability distribution of each possible output. We sample from that, and then that output goes back into the RNN. So we have a feedback loop. If you're familiar with DSP, it's kind of like an IAR filter. And then during training, we just repeat this for each training example, and we run through the training data set multiple times, and we're looking at the difference in the distribution between the training example and what we're generating and updating the weights based off that. Simple enough. So I also have a composition I wanted to share that was generated with an LSTM. So this is a type of RNN that is just a little bit more fancy than the base RNN. So it has these three different gates for get, input, and output that allow the architecture to decide what information in each step do we want to store for later, or what do we want to throw out because it's no longer relevant. So for this piece, I trained an LSTM on 400 Bach chorales, and I was really interested in this idea of like, what does a model sound like as it's training? So what I did is I saved the state of the model every half hour to use it in a performance. And then while I was playing, I could cycle through on my synthesizer the different model checkpoints. And you can kind of hear throughout the piece how it evolves from like really chaotic dissonant music to something that starts to resemble like tonal harmony. So I'll play something from the beginning of the piece that I performed. I think probably Bach would not be very happy with that. But then if you move to some of the later model checkpoints in the piece, you can start to hear it's developing a sense of like harmony. So I don't know what Bach would think about my instrumentation, but I feel like he might prefer some of the harmony here to the beginning, even if it's not perfect replication of Bach. So now I want to talk a little bit about how we represent musical data in some of these models. So in a lot of the examples that I've shown so far, we're representing music in a symbolic way. There are a lot of different ways you can symbolically represent music. Top left, we have a score. This is what if you play a traditional instrument, you're probably familiar with reading music from this. There's also MIDI, which is how a lot of different synthesizers communicate music. If you're a guitarist, you've probably played from guitar tabs on the internet. And then the top right is music XML. So all of these are really compact, readable representations of music. you could represent like a minute of four voices of eighth notes in 5.7 kilobytes, which is super small, but it doesn't give you any timbre information or any information about the articulation. It's really just what notes are playing when. And then if we contrast that with the audio representation of music, we have two options. We have the waveform domain where we have a sequence of amplitude values. This is like the closest you can get to the raw sound, but it's hard to discern the musical information here. And here, instead of kilobytes, 1 minute of audio is 10 megabytes if you're doing full fidelity sample rate. We can also think of representing music as a spectrograph in the frequency domain. So if you take an FFT of it, and this is nice because it shows us more about the harmonic properties of the music, the timbre, and complex frequency information. But again, it takes like a lot of data to store this. But there was a little bit of work done in like 2018, 2019 about audio space RNNs. One example is sample RNN, which was a hierarchical RNN that operated on like these three different levels. There was like the frame level, which grouped samples together. Then there was a smaller sample level RNN and then an MLP layer. And this is actually used by an artist I really like, Holly Herndon. So she created an AI trained on a bunch of different vocalists that she called Spawn. She described it as an inhuman intelligence housed in a DIY souped up gaming PC. And she said that it placed an emphasis on alien songcraft. So this is a really cool album. She uses sample RNN a lot in it, but I'm just going to play a sample. So this piece was trained on the voice of someone beatboxing, and you're going to hear it sounds pretty weird. Yeah, so here I think she's really trying to like lean into the like uncanny alien nature of some of these early algorithms, which I think is really cool. There's another piece on the album where she trained it on people like call and responsing her at one of her concerts. Not all the songs in it are that weird. I definitely recommend the album. And then now let's move into the moment you've all been waiting for, which is some talk on modern music AI. So we're gonna take a step away from RNNs and start to talk about transformers. So RNNs, which we've talked about before, they're using a fixed size state to represent all of the past events in the sequence. So theoretically, it's infinite because like every step you can add more information to the cell state, but they can be kind of difficult to train. There's issues with the gradient vanishing or exploding. So I'd say these have pretty much gone out of fashion lately. With transformers, the idea of attention is really what makes these so powerful, because at every step when you're predicting a token, each attention head can assign different levels of importance to every other event in the sequence. So you kind of have this like direct association between the current token and how important all of the other tokens are. So it makes it a lot better at modeling long and complex dependencies. But the downside of it is that the context length is finite. You can't keep going forever and ever like you can with a traditional RNN. And then let's talk again about another big thing, which is how we encode audio. So as we talked about before, audio is really expensive to generate and store compared to the symbolic representations. So at 44.1 kilohertz, you'd have to be generating 44.1 thousand samples every second. And in the frequency domain, you'd have to be generating like probably around 512 samples 86 times a second. So that's not very efficient. And maybe there's a better way we can be more clever about how we store audio. And if we think about like things that already exist, like MP3 compression has been around for a while, and that achieves a like a 10x compression ratio compared to WAV files. So maybe there's something similar to that we can use for audio generation. And it turns out that is definitely true. So similar to how we can train a neural network to classify or generate something, we can also train one to learn an optimal compression format for audio, and we can use unlabeled data. So usually these models are made up of an encoder and a decoder. So the encoder compresses the audio, and then we might have a generative model that's outputting in that compressed space. It could be either continuous or discrete. And then we have a decoder model that reverses that compression to translate the model back to audio. Now these definitely aren't lossless, like there's still some information loss in this, but we can perform a lot better than MP3. So we're greatly reducing the computational requirements of audio generation because we're reducing the data size that we're working in. So high quality MP3 is like 300 kilobits per second, waves about 1500, which is a lot. But with models like this, we can get similar quality scores to an MP3 at a much lower data rate. So you can see here, comparing like this SoundStream architecture to Opus, the bit rate is much smaller, but the score is much higher. And this is like kind of an older paper this is based off of. This is from 2021. All right, and then let's talk about how we actually do the music generation now that we've learned a little bit about encoding formats. So a popular paper that came out a couple years ago is Google's Music LM paper. So what they're doing is encoding text and audio into a shared embedding space to train a text-to-music model. So for instance, this is one of the prompts that they provided on their website, and here's the output. Oh, very loud, sorry. And let's talk a little bit about their architecture during training and test. So they're using this model called Mulan to represent text and audio in this shared embedding space. So basically, you can compare the similarity of a piece of text to a piece of audio. And because they're doing it this way during training, they can pass in embedding tokens of audio to compare that to the output, but then during inference, they can instead pass just the text itself to get the output. And another interesting thing they're doing here is when they are representing the token space that they're generating in, they're breaking it up into semantic and acoustic tokens, where semantic tokens are generated by this model that's focusing on more higher level features like notes, chords, rhythm, that kind of thing. And then there is another type of token called the acoustic token that's focusing more on like the timbre and audio quality. So these together make up the tokens that this model works with. And we talked a little bit about this idea of text conditioning. So this is a paper called Mulan that came out a couple years ago, and it's mapping audio and music into the same embedding space. So, you know, text and audio that are similar to each other are going to be close to each other in this space, and it's trained on a bunch of pairs of text and audio descriptions. And what's nice about this is we can compare vectors in this embedding space for similarity, and this allows us to prompt a model like Music LM with audio or text. And the nice thing about this is that during training for Music LM, we can actually train on unlabeled data because we have this embedding space. So we don't need exactly like a description of the audio we're training on. We're just putting it in this embedding space. And then next up, we're going to talk about diffusion. So I'm sure a lot of you have heard about like stable diffusion for image generation. It's pretty different from transformers, but basically the idea is we're generating an image or audio by gradually moving noise from an initialized state. Then these types of models also support text conditioning to steer the denoising process. Like with Music LM, they'll usually use an embedding space like clip for images to map text to like a semantic embedding space. So during training, you can see we're adding noise and taking a fully done image and turning it back into noise. And then during inference, we're trying to learn how to remove the noise. And this has been done in audio as well. So Stable Audio, which is the same company that launched Stable Diffusion, also has an audio model. So similar to Clip for text and image embedding spaces, there's also Clap for audio embedding spaces. So they're using that to support prompting. And then they have this UNet architecture with cross attention that allows them to attend the text prompt, sorry, to attend the output to the text prompt embedding. And they're starting as noise in the latent space, which then gets decoded to audio. So we can listen to output from them. Yeah, and so let's talk about some differences between these architectures. So both transformers and diffusion are text promptable. Transformers, they have variable length outputs. Diffusion, you're generating a fixed length. For transformers, they usually require you discretize the input tokens, whereas diffusion, you can work in a continuous latent space. For transformers, the generation is sequential, so the past inputs is influencing the future, whereas in diffusion, you're generating a whole chunk at once. Transformer is usually memory bound, and diffusion is usually compute bound. Um, all right, kind of sped through that, but we're short on time. All right, let's get to the fun part, which is about using Suno as a musician. So, we put a lot of work into training our models to generate good music, and then people use them like this. Some of these are my prompts. So we launched a weirdness slider that when you turn it up, basically makes your output sound like it's gone through a like food processor. A lot of people love it. People love to prompt with things like classical Baroque and dubstep and things like side haircut, which I probably don't think is in our training data. Prompting for genres with decades they didn't exist in, like techno from 1940. A lot of people will do things like rather than type lyrics in, they'll just like type weird sound effects like on the upper right and get stuff. Um, Suno also supports negative prompting, and I like to prompt with minus music, minus notes, minus harmony, and minus melody, and that gives you noise. Um, and yeah, people will do things like use inline tags to get like a piece that starts with avant-garde opera and then turns into like a house bridge. So like, sure, there's people who are going to use Suno to generate like a fun song, for their cat, but I really like when people use it like this because I think it's really interesting and it's something that you can't do like without AI. Yeah, so let's get a little bit into Suno terminology. So, and a couple of fun use cases. So, I think a lot of people know Suno as being a text to music engine, which is true, but there's also a bunch of other things you can do. We have a cover feature, which allows you to recreate your song in a new genre, keeping like melody and harmony elements from the original. We have a persona feature that allows you to create a new song with the musical style of another track. So, if you have like an instrument or a vocalist you like in one Suno track, you can generate another song that might fit on that same album. You can also extend from any track. So you can regenerate from any point in a song, and optionally, you can change the style. So a couple of fun use cases I really like are you can add cool surprise to tracks by extending them into a different genre and then trying to take them back into the original. I really like to use covers to mash up genres, so like taking melodic ideas from one style and transforming them into a new one. Or you can use a persona to create a cohesive set of songs that share a vocalist. And now I'm just going to go through a couple of pieces that I've made with Suno. So the first one is called Mechanical Dream. So I'm just going to go through the playlist and talk about it. So I'm a classical guitarist. So for this piece, I was like, I want to do something that's classical melody, but also is like electronic. So I started out generating some Spanish classical guitar, and I really liked this one. But then I like that melody, but I wanted an electronic piece. So I used the cover feature and started prompting with like electronic Rhodes experimental glitchy modular synthesizer. And I thought that was really cool because it kind of sounds like this electronic music box, and I wanted to lean into that idea, but it's pretty sparse. So I started using extends to like pick up the intensity of it. So for this first extension, I added in like electronic drum kit, percussion, groovy bass, techno, and got this. That was okay, but I wanted something that got like even more intense later than in the song. So I extended from that again. And thought that was really cool how it kind of sped up at the end. And then I was like, okay, I want to lean into this music box idea. So I need like some sound effects of like someone turning the music box. And that's where we get to this. It's literally just noise piece where I tried to get Suno to generate noise, even though it really doesn't want to do that. So with negative prompting, I was able to get this. So I think it's an app description. Like that's literally just noise. And I was like, great, those are cool textures. I'm going to use that. So I took this back together and stitched everything together in Ableton. I added a couple like melodic and harmony and drum lines to turn it into a full piece. And I played around with like reversing pieces to give it a more glitchy feel. And I put in some of the textures and then ended up with this is the final result. I'll play a little bit of it. We'll skip forward a bit. And then the speeding up. Yeah, so you get the idea. Basically, what I'm trying to stress here is that Suno isn't just like you type in a sentence and you get in a song. There's a lot of ways that you can use it to like spark your creativity and create things that you then build off of in a DAW, create something that really does truly feel like yours. One other example I'll go through quickly. Okay, so maybe we'll do questions then. Yeah. Okay, we'll stop there. Let's skip through a little bit. Oh, yes, we have a student code. If you'd like to try out a month of Suno Pro, you can use this code. Let me actually put it on the next slide too. Oh, no. Okay. Yeah. So thank you guys for listening. You can find me on the internet. That's my website. You can check out my Suno profile where I posted more of the songs we didn't get a chance to listen to. I post my music on Instagram and feel free to email me with questions. Yeah, I'll have a couple minutes at the end for questions now if anyone has anything. Yeah.
What do you see Suno doing next?
Well, I can tell you what we're doing immediately next, which is we recently announced that we're launching Suno Studio, which is going to be kind of like a web-based DAW experience. So rather than the typical text to music interface, you'll be able to like build up a composition from the ground up using Suno tools. So really excited for that. Mostly things that give, I'm really excited for things that give people more control, make them feel like a song is more theirs rather than they just like wrote a sentence and got an output. So any sort of like DAW feature that musicians are already comfortable working in, I'm really excited about that and MIDI, which we're working on. Yeah.
Is Suno planning to have an offline feature?
Oh, not that I know of. Yeah. Yeah.
For like individuals, it's like a really big tool, but do you see this like ever being a thing in like short films or like movies for like background music that like directors they could use instead of like studios?
Yeah, I mean, I think we're reaching the point where this technology is really powerful and musicians are going to be using it in their projects. I see that happening like in their own compositions, in films and video games, like I think across the board. Yeah. I don't think it's like quite there yet, but I think there's a lot of potential. Yeah. Yeah.
How is like music IP protected, you said?
Yeah, I can't talk about any sort of like legal stuff on our training data. I guess what I can say is if you have a Suno free account, you don't have commercial rights to anything that you create, but if you have a Suno Pro account, we give you full commercial rights to everything that you make. Yeah.
Do you ever plan on, like, suppose the user wants to input a scene and they prompt them to put like a cover over it musically? And so like the director has some shot and they want to overlay it with some sort of music and they get a feel of it. So, gonna try to dabble in that sort of cinematic place.
Yeah, so you mean like music generation for a video? I can't say anything specifically. It's a cool idea though to do like video-based music generation. Yeah. What's up?
Still hiring.
Yes, Suno is hiring. We're hiring across the board. So if you're a software engineer, we're looking for ML people, designers, all that kind of stuff. Come talk to us at the sponsor booth. Yeah. Okay, cool. That's all I got. Thank you guys.
Oh,